Hello everyone, welcome to our channel OnlyPhysics Grad. So today we'll be discussing JEE Advanced PYQs from the chapter Current Electricity. This will be the first video on this chapter, and the topics will be covering Ohm's law, resistance, and resistivity. There will be 27 questions we'll be discussing. So let's start with our first question. So we have infinite line charge, a uniform line charge density lambda lies along the axis of vertical of an electrically conducting infinite shell. So we have like this, okay, and we have a line charge like this, right? Now this shell is electrical conducting, okay, of radius r. So its radius is r. At the time t equal to 0, the space inside the cylinder is filled with a material of permittivity E. So it is filled with some material, okay, whose permittivity is epsilon. And okay, so other half of the question must be this, right? Now, and of electrical conductivity sigma. The electrical conduction in the material follows Ohm's law. Okay, so we have to apply Ohm's law here. Which one of the following graph best describes the variation of current density at any point in the material? So look, first of all, we need to understand if there will be conductivity. Look, it has some charge q, okay, so we can say like the charge q it has, but actually as it is infinite, so we cannot define a q, so we have to just only say that it has a linear charge density lambda. That means it has some charge, so not, instead of writing it as a charge q, we'll say it has some charge, okay. Now, as this material is conducting, so charge starts to flow in the outward direction, right? It should flow like this. And due to this flow of charge, we will have some current, right? So as the time passes, this start to flow, the charge on this wire will decrease and hence current will decrease. So look, all the graph showing the current density decreases. We know it will decrease, but how it will decrease, we have to solve. Okay, so let's start. So look, let's first consider some integrating element. Look, the electric field due to this will be in this direction, right? So electric field will be in this direction. Look, if we have to find the current, it is V divided by R, right? So we know R, but we don't know V. So for V, we have to find the electric field due to this, right? So at any point of time, the electric field will be like this. This we have a wire, and electric field will be like this. And it was 2k lambda by R, right? At a distance small r, 2k lambda by r, and where 2k will be 1 upon 4 pi epsilon will be there, right? Lambda upon r. So it will be, electric field will be lambda upon 2 pi epsilon r, right? So we'll not write it as epsilon naught because the material is, its permittivity is epsilon, so we'll write epsilon, okay. So look, this we know, right? So if you want current, so look, the current will be like this in the outward direction, but integrating element, we have to take it as a circle. So let's say this is our cylinder and this is our integrating element at a distance r. So this will be like this, okay, of the thickness dr. Now the current is passing through this dr, right? Current is passing through this dr, and the area will be, it will be 2 pi r dr. Okay, so let's just put it here. So current will be V. V will be E into dr, right? So it will be E into dr divided by resistance will be resistivity length, so it is passing through dr upon area. So area will be what? Look, the area we have to take is the skirt surface area. Okay, we knew that the current which is passing through, it is passing through this distance, and the area we have to take is the perpendicular. So this integrating element should look like this. Okay, so this integrating element should look like this. So this is our h. Okay, this is 2 pi r, this is 2 pi r into h. So area will be 2 pi r into h, right? And now we know conductivity is 1 by rho. So at the place of rho, we have to write 1 upon sigma. So dr will get cancelled. So it will be E into 2 pi r h upon, this is 1 upon sigma. So it will be, sigma will go. Now E, let's just put it here. So it will sigma lambda upon 2 pi epsilon r 2 pi r h. So 2 pi r will get cancelled. So we'll simply have rho sigma lambda h by epsilon. Okay, so this is our current. Now you will say, sir, it is constant. Look, lambda is constant, h is constant, sigma is constant, E is constant, right? But no, it is not. Why? This lambda will change, right? Lambda is what? Charge density. So as charge start to move in the outward direction, this lambda will decrease. So this lambda will change as the time passes. So we need to find this lambda. Okay, right. So look, we have current and we can write current as dq by dt. This will be equal to sigma h lambda upon epsilon. Okay. Now, what can you write q? So q for this integrating element. This was our integrating element, right? So this was integrating element. Now look how much the length it is having. So it is h. So charge it will be having, this wire it will be having, it will be lambda into h. So let's put it here. So d by dt, and the q will be lambda into h, right? So it will be sigma h lambda upon e, right? So h will get cancelled, and we have d lambda upon lambda equals to sigma upon epsilon into dt. Now, as the time passes, as the time increases, dq decreases. So I have to put a negative sign also, right? Now, if you integrate it, we'll get lambda ln log n log lambda, right? Into minus sigma t upon epsilon. Okay. Now, if you put the limit at t equal to 0, it is, let's say, lambda naught, and after a time t, it will be lambda, right? So we have ln lambda upon lambda naught is equals to sigma minus sigma t upon epsilon. Okay. Uh, so epsilon is in denominator, right? Okay. So we have lambda will be equals to lambda naught e to the power minus sigma t upon epsilon. Okay. So we got this lambda. Now what we have to find? We have to find the current density, right? So current density will be, it will be I by A. It will be I by A. Now let's put all those things here. So I was sigma lambda. In the place of lambda, we'll write lambda naught e to the power minus sigma t upon epsilon into h upon e. And in the place of area, we'll write 2 pi r h. Okay, so h will get cancelled and j will be, this is constant, right? So yes, we're doing it correctly, right? Okay, so it will be sigma lambda naught upon 2 pi r epsilon e to the power minus sigma t upon epsilon. Okay, so this r is a variable and t is also variable, so this j is basically r comma t, right? So this is the current density at any point which is at a distance r from this line and at a time t. So we do not need r, so we'll just consider it as a changing with t, so it is changing exponentially, it is decreasing, right? So which option is correct? So it is a, right? It's this is also exponential, but it is saying after t infinite it will become some like 1 ampere per meter square or something, right? But it will, if time becomes infinite, this becomes 0, right? So a will be the correct. Okay, now, so this was quite interesting, and of course it was a moderate question. Okay, so let's move on to our second question. So this is the other half of this question, right? So we have, to verify Ohm's law, a student is provided with a test resistor. So we have a test resistor about which we have to prove the Ohm's law, a high resistance R1 and a small resistance R2, and two identical galvanometer and a variable voltage V. So the correct experiment. So look, we know to verify Ohm's law, we need a voltmeter. Okay. So voltmeter how will form? We'll take a galvanometer and we uh, connect it with a resistance which is quite high. So we have a high resistance is R. So this becomes our voltmeter, right? And we will connect this voltmeter the parallel to our test charge. Okay. Now we need a ammeter also. Why? Because we need current. Okay. So how we'll make ammeter? We'll take a galvanometer and we connect a very small resistance parallel to it, right? So this was R2 and it will connect this circuit in series. So this will be like this. Okay. So this is our ammeter, right? So we'll just connect like this. So this is our R2. Okay. So we have to find this type of circuit and the voltmeter is this. So I'll just rub this part. I'll rub this part and I'll just put like this. So like this. Which option is correct? So in the parallel to RT should be GR1, and in the series this is whole is our emitter. So C is correct, right? Okay, perfect. So quite easy question. It's a very basic question. Let's move on to our third question. So we have this. What is asking? Consider a thin square sheet. So this is L or this is also L. Okay. Thickness is T is made up of a material is resistive to this resistance between the two opposite phases shown by the shaded area in the figure. So in this, so so we'll take integrating element at a distance x, and this will be our integrating element, right? Okay, of thickness dx. So resistance will be, so small resistance will be rho into dx and area. So area will be T into L, right? T into L, and we'll integrate it. We'll integrate it. So resistance, because these small resistances will add up, they are in series. Okay, so will add up like the simple geometrical sum, algebraic sum, right? So we have rho upon T into L, and integrating of dx will be x from 0 to L. This is L, right? So we have rho L upon T. L will get cancelled, right? So this is rho upon T. So resistance directly proportional to L, it's wrong. Directly proportional to T, it's also wrong. Independent of L is correct. It is independent. Independent of T, no, it is inversely proportional to T. So C is the correct option. That's okay. So let's move on to the fourth question. So we have circuit like this. Okay. So we have to find the current through this 2 ohm. So it's a easy question. Let's say it has I1, and if you use Ohm's law, then the I1 will only flow in this circuit. And if you consider like here, this is I2, and I2 will only flow in this circuit. So in this circuit, in this part of the resistance, there will be no current, right? Yes, because this 10 volt will drop here if you try to find I1, and I2, this 20 volt will drop here. So there is no voltage drop. Means this point and this point will be at same resistance, same potential, and the current will be zero. So it's a very easy, nothing we have to do here. Let's move on to the next questions. Okay, so this is our fifth question. So this is a quite simple question, right? We have a copper and germanium. So one is conductor and another is semiconductor. One is conductor, other is semiconductor. We know in conductor resistivity increases as you increase the temperature. This is in conductor, right? Because they have so many carriers, and due to increase in temperature their collision will increase, due to which relaxation time will decrease. Okay, hence resistivity increase as you increase the temperature. But in semiconductor, as there are very few of charge carriers or free carriers, so on increasing the temperature actually resistivity increases. Okay, so it should be like this. The implies should be like if T increases implies resistivity increases. Okay, now again come back to semiconductor. So if the temperature increase, as they have very less number of free carriers, so if we increase the temperature, resistivity actually decreases. Okay, conductivity increases, right? So you can think this as a like a road. So conductor is a road. It's a road with full like full traffic. Okay, bumper to bumper traffic is there. Okay, so it's a road with full traffic. Okay, and in for the semiconductor you can consider it as a road with very less traffic. Very less traffic. Okay, so what happens if you increase the energy? Means like you bring a car, you take a car and give it energy. Okay, so what will happen? It will collide with a car in front of it, and the front car will collide another, and this will cause a chaos. Hence resistivity will increase. Okay, for the semiconductor you can consider road with a very less traffic. So what will happen if you take a car and like push it on the road? It will not, the chances to collide with the other cars will be very less, because this road has very less traffic. Okay, so actually conductivity will increase, hence resistivity will decrease. Okay, so in the copper strip resistance will increase, right? So okay, it is cooled, so we have to take in the uh, opposite way. So if temperature is decreased, then resistivity will decrease for conductor. Okay, and the temperature is decreased, so resistivity will increase for semiconductor. Okay, so temperature decreases, copper strip, the resistance of copper strip will decrease. So this C option is correct. And germanium is. Okay, quite easy question. Let's move on to 72. So this is quite easy, I think. This is our sixth question. So 6 resistors are equivalent resistance. Okay, let's find first between P and Q. So this is P, this is Q. We have a resistance like this R, and look, all those three are in parallel. So this is R by 3 and this is R by 2. They are in series. So we have these two resistance in series. This is R by 2, this is R by 3. So if you add them, it will be 5R by 6. And this 5R by 6 and R is in parallel. So we have R equivalent as 5R by 6 into R upon sum of them. So sum of them will be 11R by 6. So R will get cancelled, 6 will get cancelled. We have 5R by 11, right? Right. So this is R equivalent about PQ. Now about QR we can also find. So it will be this R and this R by 3 is in series. So we have a resistance R and this is R by 3. They're in series and they are in parallel with this. This is R by 2, right? So this is between Q and R. Okay. Now we can find R equivalent about QR. It will be, so this is 4R by 3 and R by 2. So 4R by 3 into R by 2 upon sum of them. So sum of them will be 8 plus 3, 11 R by 6, right? Okay. So 6 will get cancelled, R will also get cancelled. So we have 4R by 11. So of course the D option is wrong. Okay. And currently PQ is more than QR. Let's find the last one. Which one it is? It is PR. So PR is like this. So this is P, this is R. Between PR, this is R by 3. So this resistance will be R by 3. And this is R and this is R by 2. So they are in series. So this is R and this is R by 2. So it is 3R by 2. So R equivalent about PQ will be 3R by 2. This is 3R by 2, right? 3R by 2. And this is R by 3. So I have to multiply by 3 and then we'll add them. So if you add them, it will be 9 plus 2, 11 R by 6. So 6 will get cancelled, R will get cancelled. So it will be 3R by 11. So which one is the maximum? PQ is the maximum. So which option is correct? C option is correct. Okay, so quite easy question it is. Let's move on to our seventh question. So we have a question like this. So again, this is a question where it is asking which of the following circuit uh, should verify Ohm's law. Okay. Now again, look. Uh, so we have a certain situation here. We have to analyze each one of them. So one thing is clear, this voltmeter should be connected in parallel, right? Parallel to the resistance. And this ammeter should be connected in series to the resistance. Why? Because the ammeter will give us current and voltmeter will give us voltage, and then we can verify the Ohm's law. Okay, perfect. Let's move on to our option A. So look, let's say this is our resistance R. So this V is connected in parallel with the R, right? Because the potential, so how will you know that it is connected in parallel? The potential difference across it should be same. And how will you know it is connected in series? So like there should not be any junction in between the ends of the connection. Okay, so the current should flow, I mean, right? So current should flow from a resistance to directly to the ammeter, right? Okay, perfect. Now in this case, like look, the current will go here and voltmeter has a very high resistance, so the current will pass through the voltmeter will be negligible. So simple, this I current will go like this. So I will go like this and it will divide here. So let's say it is I1 and let's say it is I2. Okay. And then I will go here from this. right? But the problem is we do not get the I2 here. Okay, so we have to check this option, right? So we need I2, right? Because the potential across R we get from voltmeter, but the current I2 we didn't get because we'll get the I from this ammeter. Okay, so we have to check this option again. Let's move on to this option. So look, I went from here, so it will go like this. So it will divide, right? So let's say it like I1 will go here and I2 will go here. So I2 will go here. So again the same situation, we didn't get the I1, right? So we have to check this point again. Now here, this voltmeter is connected like it is not even in series or parallel, so this is wrong. And this ammeter and voltmeter, again the same situation, this is also wrong because this voltmeter is nowhere near the parallel, right? Okay, so A and B we have to choose. Okay, look, so this resistance R is variable, right? So what will happen? Let's decrease the resistance. Okay, let's make this resistance to 0. Okay, so what will happen? All this current will flow from this, but we'll get the voltage, but M from ammeter will not get anything. So this is wrong. Let's go right here. So if okay, so not 0, let's make this resistance to infinite. Okay, so in this case, let's make the resistance to infinite. What will happen? All this current will go from here. The I1 will be 0. And if all the current will go here, then ammeter will show us the right current. Okay, because this current will be going from this, and voltage will also get. So A is correct. Okay, look, if you see this without applying any condition, both A and B shows that they are wrong. But as soon as you make this variable resistance to infinite, then this current, this circuit will show that it will be able to verify Ohm's law, right? But this will still not be able to verify Ohm's law. Okay, so this is quite interesting question. I'll consider it as moderate because the complexity of this question is quite interesting, right? So there are many solution online. They will say that ammeter should connect with this battery in series. Okay, so this is wrong, right? Because ammeter should be connected in series with the test resistance, right? So we have to apply the condition here. So it's quite nice question. Let's move on to our eighth question. So we have four questions here. So eighth, ninth, 10th, and this is 11th. Okay, right. So, okay, this question again, as the temperature decreases, so the resistance of the copper will increase, right? So look, this question. Okay, it was in 1988, and okay, so this book has mentioned it in two times. One it was in AIEEE, and the second time it is due to it is in the JEE. Okay, so that is why. So no issue. So again, C will be the option, right? No, as a temperature, copper not it will decrease, right? So D is the option. D is the option. This time D is the option. Okay, let's see. Because temperature is decreases, then resistivity of uh, conductor will decrease, right? So D will be the option. Okay. So this question. Okay, so it's a nice, interesting question. We have a steady current flow in a metallic wire of non-uniform cross-sectional area. So let's say this is our conductor. Okay, and the current is flowing like this. So if I will enter, then I will also exit. Why? Because there is no accumulation of Q. So whatever the Q is passing through this wire, it should exit out. Okay, so current should be same even at any cross section area. So if you consider this, if you consider this, right? So I should be same. Okay. This is a basic concept. Next, what is asking? The quantities which are constant along the length. So current will be same. Okay. So D is the option. Let's check the other option. So current will be same. Current will be constant. Right. Current will be constant. Let's check the other quantities. It is saying drift velocity. So we know current is equals to NEAVT. Now what is this? This is number of charges per unit of volume. So this will be the constant, right? Because it depends on the material. So it is constant. So what happens is if A increases, drift velocity should decrease. So let's say this is area A1, this is area A2, and we have V drift 1 here, and we have V drift velocity 2 here. So as A1 is more, so V drift should be less than V drift 2. So drift velocity will change. So C option is wrong, right? Drift velocity will not remain same. So this is also wrong. Current, electric field, and drift speed. Again, this is option is wrong. Let's check the electric field. So we know the value for drift velocity is E, capital E, divided by M into tau. So tau is the average relaxation time, and it depends on temperature and material. So material is constant, material is same, so it does not change. And the temperature is also we have to take constant, right? So tau will not change. So what happens is where VD increases, it is due to electric field, right? So at point 2, let's say electric field is E2, and at point 1, let's say it is E1. So where drift velocity is more, it is due to E. So here E2 must be more than. And we know in a current carrying wire or conductor, this electric field is actually, it is also, we can point out another thing. This electric field in this current carrying wire, okay, it is actually non-conservative field, right? You should remember this. So D option will be correct. Okay, so it's quite nice question. Remember this concept always. Current in a wire will remain same, but if area is increased, well, drift velocity will decrease, hence current will remain same. Okay, and now how will drift velocity will change? The one who's has less area will have more drift velocity. It is due to electric field there. So here electric field is more compared to this. Okay, perfect. Let's move on to our 10th question. So here, this is a simple case. This is a simple question, right? So this is 30, this is 30. They are in series. So it will be 60. And this 60 and 30 is in parallel, right? So 60 into 30 divided by 90. Okay. So this is 3 and this is 2. So we have R equivalent is 20 and we have voltage of 2. So current will be V by R. So 2 by 20, it will be 1 by 10. So C option is the correct. Okay, so quite easy question. Let's move on to our 11th question. So again, this is the same question which is very easy. So we know resistivity will equals to rho naught 1 plus alpha delta T. So T minus T naught, right? So we have given resistance, so we'll simply write it as resistance, right? So resistance at T naught is what? So at 300 Kelvin, it is 1. So this is 1 into 1 plus 0.00125 T. Temperature we have to find minus. Let's put this in degrees Celsius. Okay. Or you can put it in Kelvin, the answer will be same. So let's just put it in Kelvin. So it will be 300. Look, the change in the temperature on degree scale or Kelvin scale, it is same. So delta T for Kelvin scale is equals to delta T for degrees Celsius scale. So it does not matter. Okay. That is why I've just put it in Kelvin, because the final temperature will come out in Kelvin. So you'll get the answer right. Now, at what temperature it is? Okay. So this is 2 minus 1. So 1 will be equals to 0.00125 T minus 300. So let's divide this. So we will get 1 upon, this is 125, and then 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 zeros will go. Okay, so look, this is 5 into 5 into 5. So if you divide 10 with 5, we'll get 2. So 30 will become 8. So it will be 800 T minus 300. So we'll get T as 1100 Kelvin. Okay, so which option is correct? B is correct. All right, let's move on. So they are quite simple questions, right? Let's move on to our 12th question. So we have two more questions. So this is our 12th and this is our 13th. Okay, so an aluminium bar of cross-sectional area, square cross-section area square is drilled and filled with iron. Okay, so this is iron. Now the resistivity of aluminium is 2.7 into 10 is to power minus 8 and the resistivity for iron is 1 into 10 is to power minus 7. Okay, the two phases electrical resistance we have to find. Okay, perfect. So look, if you connect, how will you solve it, right? So look, this actually aluminium and this iron, they are in parallel. Okay, let me tell you this concept. So if they are in parallel, we know the condition. If two resistors are in parallel, that means they must have same potential drop across their uh, connecting points, right? So let's say, look, if you connect it with a battery, so we have uh, this is our material like this, right? And if you connect it with battery, and similarly, this will be, so let's just copy and paste it over here, right? So this is, let's say, 0 volt, and this is, let's say, 100 volt. Now, every point on these will be at 100 volt, and every point on these will be at 0 volt. So we can say this iron part in the middle, its potential difference is 100 volt, and similarly, this aluminium part, its potential difference will be again 100 volt, right? All these points which are connected with a 100 volt have potential difference 100 volt. Similarly, this end, all the points will be at 0 volt. Hence, these two parts are in parallel. Okay, now the question will is very simple. So we have one resistance which is aluminium whose resistivity is rho L. Okay, length is same 50 millimeter. Okay, and area is what? So area we have to find. Look, the total area is a 7 into 7, 49 millimeter square minus 2 into 2. So it will be 49 minus 4 millimeter square. Okay, and we have another resistance. This is iron whose resistivity is rho Fe, which is given. Length is again the same 50 millimeter, and area of cross section is 4 millimeter square, right? So all those three things we have here. Okay, and we'll just solve the question. Okay, so in this question, if you solve, B option is correct. Okay, you just use this R equivalent is equals to R1 R2 upon R1 plus R2, and just post the value. So we'll have resistance. The formula for resistance is rho L by A. Just put those values and then you will get the answer. So it's quite easy. Okay, but this was the concept in this question, so it's quite easy. So you'll just solve because it is very easy. Let's move on to our 13th question. So this is our 13th question. I think something is missing here. Let me add it. Right. Okay, perfect. So look, we have this 13th question. What we have here is this is a circuit and potential current we have to find all those things. So let me make this diagram. So we have one resistance over here and the one another resistance, and this resistance is here. We have this resistance, another resistance, this is another resistance. Okay, now they're connected by a 12-volt battery like this, and two more resistors are here. This point is P, this is S, this is Q, this is T. Okay, now in this wire the current is I1 and in this wire current is I2. Okay, pop. So find the resistance. Okay, for the resistance we have to find the current. Okay, so we will use the concept of mirror symmetry. Okay, look about this. So let me write the resistance for each of them. So it is 2, this is 4, this is 1, this is 2, this is 4, this is 1, right? This is 2 and this is 4. So mirror symmetry is like this. About this point here and here, they have same resistance. So let's say the current in this wire is IP. So in this wire, the current will be IP. So in this wire, let's say the current is IQ. So similarly in this wire, the current must be IQ. Okay. Now in these wire, we if we get the current, then the situation will be very easy. Okay. So let's say if I2 is going in this wire, so we'll say, let's say in this wire, it is IP minus I2. Okay, this is I2, right? So in this wire, IP minus I2. So in this wire, we'll be having IQ plus IP. So let me write here. Okay, so I'm writing it here. So in this wire, it is IQ plus IP minus I2. Okay. Perfect. So in this IQ is going. So in this it will be IP minus I2. Okay. So I2 is here. So IP is here. Right. Correct. And look in the mirror symmetry, it should be like this. If this wire has IP minus I2, this wire must have IP minus I2, right? But in opposite sense. So let's use Kirchhoff's law now. Okay, Kirchhoff's loop law. So this is our first loop and this is our second loop. Let's go like this. So in this first loop, this is first loop, this is our second loop. So in loop 1, what we have here is this is loop 1. Okay, so this is minus 2IP and it will be in the direction of current, potential will drop. So this will be minus 1 into IP minus I2, and in this it will be plus 4 IQ is equals to 0, right? So this will be minus 3 IP, this will be plus I2, this will be 4 IQ equals to 0. This is our first equation, right? Now in loop 2, we have this loop. So in the direction of current, potential will drop, so it will be 2I2, right? And this will be plus IP minus I2 into 1, and this all there will be also will be plus because we are going in the opposite direction, so it will be 4 times of IQ plus IP minus I2. Wow. So if you go like this, it will be again plus, it will be IP minus I2. will be equals to 0. So let's just solve. So it will be 2i2, and so this will be minus, right? Because we are going in the direction of current, so it will be minus. So it will minus i2, and minus 2. So it will be minus 4i2. And for the IP, it is 4, 5, and 6. So it will be plus 6IP, right? Now for the IQ, so IQ is only 4. So it is 4IQ is equals to 0. This is our second equation. Now we need to find the condition between IP and I2. So let's just subtract these two equations, because look, this 4IQ and this 4IQ will get cancelled. So let's subtract it. I'll just put it like this, 6. So this is in, so let's just write it as 6IP minus 4I2 and plus 4IQ equals to 0, and now subtract it. This will be minus, this will be plus, this will be minus. So this will get cancelled, and we have this. It will be minus 9IP, right? There must be some mistake here, I think. And this will be, let's just check it again. So it will be 2i2. This is minus. This is plus, right? So this is plus IP minus I2. And this is plus 4 times of IP plus IQ minus I2. Yes, so it's correct. And this will be 1 plus 1 IP minus I2, right? So for I2, it is minus 2 minus 1 and minus 1. So it is minus 4i2. So this is correct. For IP, so it will be 4IP, right? So 4IP and 1, and this will be 6IP. So this is also correct. And for IQ, so IQ is only once, 1 here, right? Uh, yes, so it will be plus 1 IP minus this is 4IQ. Okay, so this is correct. Mm, let's check again. I think there is some mistake. So I2 is 2 and this is 2. Okay, so this is 8, right? Look, 4i2 will come here, right? So it is 8. So this will be 8, right? Okay, so we will have plus 9i2 is equals to 0, right? Now it is correct. So we can see we'll get IP equals to I2. So what this means is in this PQ and ST, there will be no current, right? So if there is no current, then our circuit will look like this. So this is 1, this is 2, and this is 3, and we can just remove these two. Okay, so this will be like this, and like this. Okay, now it's easily solvable. So this is 2, this is 1. Oh no, this was 2, this was 2, this was 4, 4, and this is 4, right? Perfect. So in PQ and ST, the current is 0. So A option is correct. So our A option is correct. So in PQ, 0 current. In I1 we can find. So look, the total resistance is 8 here, and this is 12. So 8, no, this is 6. So it's 6, and this is 12. So R equivalent will come out to be 12 into 6 upon 12 plus 6, this will be 18. So this is 3 and this will be 4. So R equivalent is 4. So if R equivalent is 4, then we can simply find I1. So I1 will be 12 by 4. It will be 3 ampere, right? So is the 3 ampere correct? Yes, so I1 is 3 ampere. Now I2 we can find. Now look, the potential difference across this hole is 12, right? So you can simplify, find I2. So I2 will be V. V is 12 divided by 6. The resistance is 6, so it will be 2 ampere. So I2 is 2 ampere. So D option is also correct. C, the potential at S is less than that of Q. So S is this and Q is this. So this is our S and this is our Q. Okay, let's find the potential. Let's say this is 12, this is 0 volt. Now, if the current through this is 2 ampere, so this point must be at 1 volt, right? Because 2 ampere is going like this. So if 2 ampere is going, so potential difference will be 4 volt, sorry. So it will be 4 volt, right? Because 2 ampere is going here, right? So potential difference must be 4 volt. So if it is 0, then this must be at 4 volt. Now, in this, the current is 1 ampere because 2 ampere, this is total current is 3 ampere. I2 is 2 ampere. So 1 ampere is going through this. So it is 1 ampere is going through this and it is at 4. So potential difference is 4 volts. So if this is 12, then it must be 8 volt. So of course, the potential at S is, what is asking? Yes, S and Q, right? So potential at S is less than potential at Q. So is this the option? Potential at S is less than. So this is also correct. Okay, right? So it's quite interesting question. I will consider it as moderate. Why? Look, in some online solutions, they will say the current in these two wires will be zero, right? But in the mirror symmetry, we cannot directly write the current to be zero. Okay. Sorry. So we should know how to get this. So by using loop law, we get this. Then we can say the current will be zero in these two wires. Okay. You cannot directly write the current is zero in these wires. Okay. So let's move on to our 14th question. So what we have here is this circuit. So it's simple circuit, right? So this is 2, this is 4, this is 4, 2. So it is in series. So this is 8. 8 and 8 in parallel is 4. So 4 will come. So 4, 2 and 2. This is again 8. 8 and 8 in parallel. So this is 4. So this is 4. This is 3 and this is 2. So it is 9. So total current will be 1 ampere. Right? So let me make the diagram. Like this. Right. So it is 1 ampere. The current in the current through the battery is 1 ampere. Now this is 9 volt. This is 3. This is 2. This is 8, 8, 4, 2, 2. So I've already written 2 here. This is 2, 2 and 2. Okay, perfect. So let's say this point is at 9 and this is at 0, right? Now we have to find the current in this and in this. Okay, so 1 ampere is going, so potential drop will be 3 volt. So if this is 9, then this must be at 6 volts. Okay, now, and in this, the 1 ampere will be coming back. So the potential drop is 2. So this point must be at 2 volt. Now, if this is at 6, this is at 2. So potential drop is 4 and the resistance is 8. So current will be 0.5. So if the current here is 0.5, then current in this wire will be 0.5 ampere. Okay. Now, if potential, now the current is 0.5 and resistance is 2. So potential drop is 1 volt. So this must be 5 volts. Okay, are you getting me? Now, so if 0.5 is going down, then from this wire, the current must be 0.5 amperes, right? Okay, so if this from this current is 0.5, then the potential drop will be again 1 volt. So if this is 2, then this must be 3 volts, right? Now, if this is a 5 volt, this is 3 volt, right? So potential drop is how much? 2 volt. So current will be 2 upon 8. So it will be 0.25 ampere. So if this from this the current is 0.25, so from here it must be 0.25 ampere. Okay, 25 ampere. Right. Now we can find. So from 3 ohm, the current is actually 1 ampere. So this is wrong, this is wrong. From 4 ohm, it is 0.25. So D is the correct option. So quite easy question it is again. Let's move on to our 15th question. So we have a circuit like this, right? Now we have to find this value of I. So current in this R bracket to an ohm. So from this, the current is I. So we have to find this I. Let's find the equivalent resistance. Now we can see this part. Let me shade this. As you can see, this part is a Wheatstone. Why? Look, this is 1 by 2, this is 2 by 4. So 1 by 2 is equals to 2 by 4. So this is Wheatstone. So we can just remove this 8 ohm. Okay. So what we have here, let me make the diagram again. So this is 1 ohm, we have 2 ohm, and this is 2 ohm, and we just removed this. So we'll have only 4 ohm, right? And we have this 6 ohm, and we have this 10 ohm, right? So let's just solve this. So how much is this? It will be 3, and this will be 6. So 6 in and 3 are in parallel. So 6 into 3, 6 plus 3. So it will be 6 into 3 by 9. So it will be 2. So this whole is 2. So look, this green part will become 2. Now our circuit is resolved like this. This is 6. This becomes 2. This is 10. This is 12. This is 4, right? And like this. So this is our R, which is 2 ohm, 6, 2, 12, 4. Now look, this again becomes Wheatstone. 2 by 6 equals to 4 by. So we can just eliminate. Now what will happen? This is 6 overall, and this is 6 plus 12, 18. So they are in parallel. So R equivalent will be 6 into 18 upon 6 plus 18. So we have 6 into 18 upon, this is 24, right? Okay. So we can just, this will be 4, right? So we have 9 by 2 is this R equivalent. And now 9 by 2 and this 2 is in series. So R equivalent of this circuit will be 9 by 2 plus 2. So it will be 13 by 2. Okay. So the current will be V by R. So V is 6.5. So 6.5 is 13 by 2, and this is 13 by 2. So it will be 1 ampere. Okay. Again, quite easy question. We have to just check this if it is Wheatstone or not. So it was Wheatstone, and then we get the answer. Let's move on to our 16th question. So we have a comprehension So, okay. So consider an evacuated cylindrical chamber of height h having rigid conducting plates at the ends and insulating curved surface as shown in figure. Okay, so this is insulating and these are conducting. A number of spherical bowl A number of spherical balls made of lightweight soft material coated with a conducting material are placed on the bottom. Okay, the balls have radius small r, so these balls have a radius small r, and r is much less than h, and this is h, right, the height of the cylindrical container. Now high voltage is connected, is conducting, so this is minus v naught and this is plus v naught. So actually it is 2 v naught, right, potential difference. Due to their conductivity, the ball gets charged and will become equipotential with the plate and are repelled by it. The balls will eventually collide with the top plate, where the coefficient of restitution is taken to be 0. So E is 0 and E is a velocity of separation upon velocity of approach. Now, if this is 0, then velocity of separation is 0. That means they stick it. Like their velocity becomes 0. Okay, the final velocity becomes 0. Soft material. Okay, the electric field can be considered due to the plate. Assume that there are no collision between the balls and interaction between them is negligible. Also ignore the gravity. Perfect. Which of the following is correct? Now what will happen? Look, so this is our plates, right? It is positively charged, it is negatively. Now as soon as it becomes positive charge, it start to rise because the electric field will be like this. So they will rise there. If they reach, so here they are at the positive charge, and here after reaching there, they will first become neutral and then they will get negative charge and they will get repelled. So they will go down. So first they will go up, then they will go down, then they will go up, then they will go down. And the situation will continue to happen till battery loses its energy, right? Till battery loses its energy. Okay. So which of the following is the balls will bounce back to the bottom plate carrying the opposite charge and they went up with. Okay. So this seems correct, right? Let's move on to next point. The ball will stick to the top plate and remain there. No, so it will come back. So B is wrong. The ball will execute simple harmonic motion between the two plates. So it look like an oscillatory motion, but we have to check if it is SHM or not. Okay, so let's find. So let's say ball 1 will get Q charge. So how much Q will be? As uh, the balls are here at the bottom plate, they will get charged like they have the equipotential. So it's a V naught. So the ball's potential is KQ by R should be equals to V naught. So Q will be V naught R by K. This is the first equation. Now on the force on the ball will be F equals to Q into E. So Q is V naught R by K. This is all constant. And electric field. So electric field will be, this is minus V naught. So electric field will be potential difference, which is 2 V naught divided by distance. So it is H. So we'll just write it as 2 V naught by H, right? And look, everything is constant. So force on the ball is actually constant, right? So it is not like this, proportional to minus x. It is not like this. So this C option is wrong. This is a simple oscillatory motion, not SHM. The ball will bounce back to the bottom plate carrying the same charge they went up. No, wrong. So it will be opposite charge. So A is correct. Okay, it's quite an easy question, but this comprehension is a lengthy to read. So there was another question on this comprehension. Let me put it before you. So it's this. Okay, perfect. So what is it asking? The average current in the steady state registered by the ammeter in the circuit will be. So let's check if it is a zero or not, right? Perfect. So look, we have this. So as positive will go up, Okay, so as positive will go up, so current will be in the direction of positive charge, so I will be in this direction. Now the negative will go down, so negative will go down, but the direction of current, the direction of current in the is in the opposite direction of the movement of negative charge, so current will still be up. So in both the situation, when positive is going up and negative is going down, right? So positive is going up, negative is going down, the current will be always in the upward direction. So the average current will not be zero. So this B is wrong. Now we have to check. So let's find this current. Okay. So we have charge Q is V naught R by K. Okay. So how will we find this? So look, this is H and we have the force. We have the force. So force is how much? So it is 2R V naught square upon KH. Okay, so K will be 1 upon 4 pi epsilon naught, right? So we have this force. Now, if they are moving with a like distance h, it is moving a distance h. Let's see how much time it will take to travel to a distance h with the acceleration this. So this is constant, right? This is constant. So acceleration will be f by m. So it will be 2r v naught square by khm. This is our acceleration, right? So let's find the time. So why I'm doing this? Because we know the current is q by t. Now the q charge is moving up, okay, and it is taking t time. So we'll just find the t. Let's find the t. T is what? So if you use the second equation, you get 2h by a, right? So let's just put it here. So it is 2h by a. A is 2r v naught square into k h m. So 2 will get cancelled and we have h square. It will be h in the out and v naught will also come out. And we have a root km upon r. So this is our time, right? And we'll just put the values here. So q was v naught r by k and time is h upon v naught root km by r. So we have v naught square r upon kh and this is a root km and root r will go here. Okay. So we can see I is proportional to V naught square. I is proportional to V naught square, right? So which option is correct? So C option is correct. Okay. So it was quite interesting question. Let's move on to this was our 16th, right? It was 16th, right? So 16th and 17 we have covered. Now let's move on to our 18th question. So what we have 18th. So this. So we have 18th, 19th and 20, right? So this is a quite simple question. I think the resistivity of a semiconductor increases with increase in the temperature. So this is wrong, right? The resistivity will decrease. So A statement is wrong. So this is simply D. Okay. Now let's move on to next question. So draw the circuit diagram to verify Ohm's law with the help of main resistance 100 ohm and 2 galvanometer of resistance this and this. So the galvanometer with high resistance is actually our voltmeter and the galvanometer with less resistance is actually our ammeter. So this first should be connected in parallel and the second is going to connect in series. So this is quite an easy question. Okay, let's move on to next. So two resistors we have 400 and 800 are connected in series with 6-volt battery. Now it is desired to measure the current in the circuit. The ammeter of 10 ohm is used for this purpose. So if they are in series, ammeter should also be connected in series, right? This is 6-volt, this is 400, 800, and this is 10 ohm. right? So what will be the reading of ammeter? So I will be equals to V by R. So R will be 1210. So this will be our current. Now we can't ignore 10 because 10 is comparable to 400, right? Similarly, the voltmeter of 10,000 ohm resistance is used to measure potential difference across 400. So this is again the same simple question. So we have to connect this voltmeter in parallel with this. So this is 1000, this is 800, right? 6 volt. Okay, this is 10,000 actually. So again, we can't ignore this, right? So let's just find the equivalent resistance between them. So it will be 10,000 into 400 divided by 10,400, right? So if I use the calculator really fast, what we'll get? So it is 10,000 into 400, right? Divided by 10,400. So we will approximately get 384.6. So we'll just write 385, and this is our 800, and we have a voltage battery of voltage 6 volt. So we can find the potential difference across this. So it will be 385 divided by sum of them. So it will be 8 11 8 5 into overall 6. So we will get divided by, I'll use the calculator again. Okay. 6 into 6. So we will approximately get 1.95 volts. Okay. So this is quite easy again. Let's move on to the question number 21. So question number 21. So we have four questions: 21, 22, 23, and 24. Perfect. So in 21, we have a steady current passes through a cylindrical conductor. Is there electric field inside the conductor? Yes. Right? And this electric field is actually non-conservative. I have told you in this video, right? It is actually non-conservative. Okay, because it completes the loop. Look, if the resistance is like this, so we have this is our resistance and it is connected with the battery. Now, as this is a conductor, there must be in the electrostatic condition, there must not be any electric field inside it. But actually, in this circuit, this is not electrostatic condition. This is dynamics, right? The charges are moving and they are moving due to electric field, right? They are moving due to electric field. Okay, and this electric field is forming a loop and it is doing work. Why it is doing work? Because the energy is continuously dissipated, right? So this E has to do some work. Okay, so that is why it is non-conservative. The loop, it is doing the work, so it is non-conservative. So yes. Next, in this circuit, this is 30. The voltmeter reads 30 volt here. So another 30 volt should drop here, right? Calculate what the same voltmeter will read if it is connected to 300. So this is quite easy, right? So from this first information, we'll find the resistance of this voltmeter. So if this is 30 and this is 30. So the current will be, so current will be V by R, 30 upon 300. So it will be 0.1. So the current is 0.1 going here. So from this resistance, how much current it will have? So it will be V 30 upon 400. So it will be 3 by 40 and this was 1 by 10. So the current through voltmeter will be 1 by 10 minus 3 by 40. So we will have 44 minus 3, it will be 1 by 40. So this is current through voltmeter. and we know voltage across it V by R of V. So simply we'll get the resistance of voltmeter as 40 into 30. So it will be 1200 ohm, right? So if you get the resistance of the voltmeter, you can find the potential drop if it is connected with 300. So how will it be? So this will be our new circuit. So this is 60, this is 400, this is our resistance of 1200. Actually, this is voltmeter, right? And this is 300 ohm. So if you find R equivalent here, so R equivalent will be 1200 into 300 divided by 1500, right? So this will get cancelled. This is 5 and this will be 5240. So 240, right? Now the voltage will be, so voltage across this will be resistance of this, it is 240 divided by sum of them. So it will be 640 into the total 60. So this will get cancelled, right? Mm, so we can 3 and this will be 32. So if I use a calculator really fast, 240 into 3 divided by 32. So we will get 22.5 volts. Okay. So again, quite easy question. Let's move on to our next question. That's 23. So all resistance in the diagram are in ohm, the effective resistance. So I think this question you must have done it many times. So we'll see. So about A and B we have to find. So these 2 points we have to find. So look, 3 and 3 is in series, right? So 3 and 3 is in series. So it's 6 and 6 are in parallel. Again 3 and 3 in series, and with the 6 they are in parallel. So again 3 and 3, again 6 in parallel with 6. So it will be 3. So we will have just, let's say this is A point, this is B point, this is 3 ohm, and we have 3 ohm, which is due to these all, and they are in series. So this is 3 ohm. So we have simply 6 and 3 are in parallel. So 6 into 3 by 6 plus 3, this is 2. So this will be our R equivalent. Okay. So again, quite easy question. Let's move on to our 24th question. So we have in the 24th question, a copper wire is stretched to make it 0.1 times longer. So L dash will be 0 L. So it will be L plus 0.1 L upon 100. So L dash will be 100, 1001 upon 1000 L, right? So we know if it is stretched, the new resistance will be equal to original resistance times the square of this. So it is 1001 upon 1000, right? Why? Because if the length is increased, then area must decrease by same proportion. So it will always come out to be square. So we'll just solve it. We will get into 0.2, right? No, so this will be, let me use the calculator. I think it was, I think it was 1.002. Yes, so let me just check it. Yes, so it was this. So how R dash is increased by 0.2%. So this is 0.2%, right? So again, quite easy question. It's a like class 12th question. You must have solved them like a lot of times, right? Even in class 10th, you must have solved these questions. Let's move on to our 25th question. So we are left with last 3 questions, right? So we have last three questions, right? So in 25, what is saying the current, okay, so IV graph is given and at different temperature, these are metallic wires. So T2 is greater than T1. Let's see if it's true or not. So we'll say, let's take some a particular voltage. Now we can see in one, like T1, the current is more than in T2. Okay. So these are metallic wires, and we know if you raise the temperature, the resistivity will also increase. That implies the current must decrease, right? So it is like the opposite. So the one which has more current must have lesser temperature. So in T1, I is more, right? So T1 must be less than T2. So T2 is greater than. So this is true. Okay, so this is true. Next, electrons in a conductor have no motion in the absence of potential difference. That is wrong. The electrons are continuously in random motion. Due to potential difference, they start to move in particular direction. So this is a false. Okay. Now the last, our 27th question. So this is a simple question. Look, this is A. Now the one end of this 2R resistance is connected with A and other end is connected with B. Okay, similarly this 2R, the one end is connected with B 2R and another end is connected with A, right? Because the potential is same. So this is V, let's say, and this is 0. So this will be 0, this will be V, right? So all those three resistance are between V and 0, right? So this is R. So all these are in parallel. So we'll simply write. So 2R and 2R are in parallel, so it will be R. So it will be R and R in parallel, so it will be R equivalent will be R by. So this will be the answer. Okay. So let's finish the today's video. We have discussed 27 questions. There will be further videos on this chapter. Okay. So thank you everyone.